proud to be introducing our second speaker, and that is Gregor Mizinski. He was born in Slovenia, studied physics, and co-founded Cozy Lab Inc. at just 21. That's a company developing control systems for particle accelerators and large experiments in physics. In 2008, he moved to become CEO and co-founder of Sinergise, specializing in software for advanced geospatial applications, helping Europe to efficiently manage and control agriculture policy, introducing land administration systems for developing countries in Africa. And with his colleagues, they recognized the potential of the open Copernicus Earth observation data early, but they hit a wall in trying to use these technologies with the large data sets. So Greg and his team decided to do something about it, and Sentinel Hub was born. This is a service for processing and distributing satellite data. It uses AWS public data sets, providing access to the data to more than 10,000 registered users, mostly web developers, creating applications on top of remote sensing data. He's worked with government clients in Balkans, Western Europe, Asia, Africa, and he's now engulfed in building a global internet business, which is currently processing 2 million requests each day. So, Gregor, you obviously keep busy. Thank you so very much for coming to spend some time with us today. We're really looking forward to learning more about your work, and I'm sure there'll be some questions. But the stage is yours, and over to you.
Thank you very much. So I'll just jump to the presentation and we can have a chat later on. I mean, I feel a bit uncomfortable after all this praise by Gilberto. I mean, I'm not sure that I can meet the expectations, but I'll give it a try. Anyway, so I'm Grega Milcinski from Sinergise, Slovenia. And I mean, Gilberto gave a very good talk on the concepts and the complexities of the machine learning in Earth observation. And I'll try to follow up on this, going a bit more deeper in the technical part. So that maybe, I mean, by joining these two talks, you can then just get ahead and start working on that. So anyway, let's start with the data, which is kind of essential part of that. And the Earth observation data is here for a while already, for decades literally, where you had the digital globe, which is now called Maxar and Airbus, and they were selling the data to governments and the scientists. But I think what really kickstarted the process was when the USGS decided to open the Landsat archive in I think 2000 something. But then what really revolutionized the world is when Sentinel-2 was launched in 2015, because it just got a bit just the right resolution and the revisit time that it really became useful, not just for science, but for many other use cases as well. And now we have tons of satellite imagery providers, not just those that are listed here, really have lots and lots of them. So, and this is now really changing, I think, also our planet, not just this field. Talking about the data, I mean, if you are new in the field, you'll probably meet this, right? I mean, you separate them based on those which are free and open and those that you have to pay for them. And then maybe whether they're optical or radar data. And with optical, you will typically start with Sentinel-2, which is a really cool data set, 10-meter resolution, every 5 days, new image. Then Landsat 8, a bit worse, and then Landsat 5 is very good because you have a long time series going back to 84. Then there are Sentinel-3 and MODIS, which are cool because they are daily. I mean, the resolution is not comparable to Sentinel, but still you can get quite a lot of information from this, and you can get them on every day, right? Then you have radar data, such as Sentinel-1, again, most commonly used. In resolution of 10 or 20 meter, depending really how you count. And you have the data every 6 days in some parts of the world and every 12 days in other parts of the world. So these are, I mean, these are, let's say, the most common open one. And then in commercial part, what you see is that you have much better resolution there, right? Going back down to 30 centimeters for worldview, half a meter Pleiades, and so on and so on. That being said, there is a significant difference between these two kind of data, is that the very high resolution are not capable of monitoring the data on a regular scale, like, I don't know, every few days or so on. So the data are only basically taken when there is some demand for it. And if you take a typical area, I mean, random area in the world, and you check how many, I don't know, Pleiades scenes are there, you would maybe get a couple, maybe 5, maybe 10 per year, but that's more or less it, right? I mean, obviously you can always decide to task the satellite to get the imagery for you every week or whatever, but then this will get very expensive. A bit of an exception in this part is PlanetScope, because it actually is able to monitor the data on a daily scale, but again, you see the resolution is 3 to 5 meters rather than half a meter and so on. Now, working with the satellite data, you will face quite some challenges. First one is the resolution. I mean, here you see a spot, a satellite image. Spot is 1.5 meter resolution when you punch sharpen it. And I mean, when you look at this image, you find it kind of familiar. Maybe you see that it's not as sharp as what you would expect because you are spoiled by Google Maps providing very high resolution more or less everywhere. But if you look at Sentinel-2 and Landsat data, I mean, this is a completely different segment, right? And I mean, we get tons of questions from our users saying, oh, why their images are not sharp. I mean, they are not sharp because the sensor is not capable of taking this kind of resolutions. So, I mean, you need to learn how to work with these different resolutions. Then the next one is are the clouds, right? I mean, yeah, you have 5 days revisit cycle, but if you take a look at these 5 days, you'll see that many of the scenes are not visible at all because of the clouds. Many are just obscured partly with clouds. And if you don't learn how to mask clouds very well, you'll have a trouble because your signal will be distorted by all these white spots or shadows or whatever. And you'll have a hard time finding anything, even when the images are not cloudy. So that's another of the challenges. Then you have a geometrical accuracy. You see how the image is like twitching a bit. That's because the georeference of the image is not perfect, right? I mean, it got better in the last years, but still you see that the pixels are moving a bit, and you simply cannot expect that one pixel will always represent the same part of the world. That's just something that you have to take into account. Now, if you work with the radar data, I mean, that's just a completely different beast. It's difficult to understand anything what you actually see there. So maybe sometimes it's better not to even bother about what you see there and just treat it as one signal that you use in the process. Then there are technical challenges such as that I mean, whatever data set you take, you'll probably have petabytes of data available in different formats, JPEG 2000, GeoTIFF, NetCDF, HD5, lots of different stuff that you don't want to bother with, different coordinate systems, and so on and so on. You have scenes which you need to stitch and so on. I mean, it's really lots of technical things. Now, there are some problems that were solved by cloud. So, I mean, you have clouds making trouble, but then also cloud helping a bit. And one very important one was that lots of these data are available on a couple of clouds, not just Amazon, also Google Cloud and Diasis here in Europe, where the cloud providers are storing the data and you can easily access them when you are in the cloud. So at least you solve this problem of storing petabytes of data. Still, you will have to solve all the technical issues. And this is where the Sentinel Hub came along, is that trying to really simplify this thing by making a harmonized API, which kind of hides all this complexity of different formats, a large amount of data processing, all these things. And behind an API, which you can simply integrate in either GIS application or machine learning workflow, right? So one API that you simply integrate. Now, if you are really just starting in this field and you are not familiar with the data, I would recommend that you just head off to the EO browser. This is one of our applications, free of charge. You can go anywhere in the world, look at what data are available, look at it at full resolution or zoom out a bit. Do the time lapses. Time lapses are a very nice way of kind of getting the feeling of the data over some area. And here you see how much of these are simply too cloudy to actually make any value whatsoever. And then another thing that it's useful to take a look into is the statistical analysis, because that's also commonly used in machine learning, where you don't look at actual images, but rather you look at the statistical representation of these sensor values over time. Now, you will have to get familiar with various vegetation indices, false color, true color, these kind of things. Again, something that you can play around here in the EU browser as well. Now, if you want to go deeper into this kind of indices, I would recommend to go to this GitHub repository where you'll find hundreds of them with some links to the actual scientific papers as well as the actual script that you need to make use of one of them. Now, the API itself is a simple RESTful API where you say, I would like to get the data in that area for that time period, for that satellite, with some parameters if you want, and you simply get the data either as rasters, like with the reflectance values, or as image if you just want to use the image recognition, or the statistical values in a JSON, and that's sometimes much more easier to work with because you have orders of magnitude less data to process, right? Instead of, I don't know, 1 gigabyte of data cube, you have maybe 1 megabyte of a JSON file. Now, you will find most of the open datasets supported there, as well as commercial, but obviously for commercial ones, there is a license fee to pay. So it's a bit more difficult to work with that. I mean, just for the cost point of view. Now, going into machine learning part, I mean, that's something that Gilberto also mentioned. I mean, you have most of the times you see the representation of specific feature, in this case, let's say crops, by this kind of vegetation cycle or pattern or whatever over the year. And I mean, you can kind of, I mean, be familiar with that because that's, I mean, this is related to the vegetation growth cycles, right? But now, if you take a look in the reality, you see that it's not as simple as it might look on that chart, right? I mean, here we see almost certainly exactly the same crop in all these fields, yet you see that the patterns are quite a bit different. So therefore, when you train a model on one field, you have no way of knowing that it will work on other field as well. And this is a small area, like in Turkey, what is it? A couple of square kilometers. If you take this to Brazil, for example, it will yet be completely different cycles, not just because it's of the southern hemisphere, but also because of the different climate conditions. So it's difficult. Now, so we talked about the data quite a bit. And now on the other side, you have the technologies to work with in machine learning. And here, I mean, there are lots and lots of tools available, open source ones, TensorFlow, MXNet, Keras, that are, I mean, really well developed tools by large players, and they're super great. Yet, what they are not is they are not fine-tuned for remote sensing. I mean, you have image recognition, you have face detection, you can recognize cats and dogs on a Facebook images, but if you want to work with multi-temporal and multispectral data, you'll probably have a trouble doing that. This is why we developed the EOLearn, which is a Python library, open source MIT license, so really as unrestricted as possible, which kind of bridges the gap between these two fields and makes it possible to prepare the data, to arrange the data in a way that they fit into the machine learning model. So you do all these, I don't know, cloud removal, gap filling, interpolation, whatever is needed, so that you can then put it in one of the tools. I mean, we didn't reinvent the wheel, we really just integrated all these good tools together so that it's easy to work with. Now, talking about the data cubes, which Gilberto mentioned as well, this is how we kind of imagine this, is you start with this part, right? You have the observations over time, and lots of these are cloudy, which you need to clean up. You need to remove this, otherwise they will just distort your model. So then you just remove this data and you end up with something like that. But then you have a non-harmonized data cube because some of these observations will be completely missing, some just partly missing. And if you want to, I mean, this will technically represent a trouble, right? If you put it in one of the typical tools. So what you typically need to do is create a interpolated feature over time. And then this fits very nicely into these tools, right? Now, one of the tools which help with that is batch processing, which was developed on top of Sentinel Hub, which basically is really fine-tuned for machine learning. What you do is you define your algorithm on what you would like to do with the data. I mean, similarly as I showed before, and then you set up a region that you'd like to work on and the time period, and then we will split this region into small chunks that are just large enough that the machine learning tools will be able to work with them. And then we'll just go on and do this. And it may take a couple of minutes or maybe a couple of hours, depending how large the area is. and you'll end up with the data that then you can just run your models on top of it. That's one example of this kind of models that is harmonized over the whole world. And I mean, this data set, what is really nice is that you can train a model in one part of the world and then try it on another part of the world, and then just see how complicated these things are and how good they will work, right? I mean, yeah, maybe they are 97% when you look at them in some small area, but as soon as you go a bit further, they will probably drop to, I don't know, 60%, and soon you'll just be rolling a dice. So the labels are super important. I mean, cannot say this more really strongly. If you have good labels, your results will be good. If you have bad labels, your results will be bad, even though maybe you'll have 98% accuracy. And it's difficult to, I mean, to some extent, it's difficult to find labels. The ML Hub is something that I would point you to. They have a collection of the open source labels, let's call them, and they are proactively working to increase the volume of this. That being said, the other place to look at are the administrative data. One of the nice things with Earth observation is that it is observing the real world, and the real world is monitored by government in quite details to some extent because of the construction permits and the planning and so on. And you can find building outlines, you can find road networks, you can find I don't know, field classifications. All of this publicly available. Probably you'll put some effort to actually get this data and to clean them up, but then you'll have tons, I mean, literally millions of labels available for a specific experiment. Some examples of the machine learning workflows. Probably the most typical one to start with is the land cover one, right? I mean, that is really probably the easiest way to start. I would recommend that you take a look in these resources. I mean, we wrote a blog post series which goes step by step through all these processes for land cover. And then you have a Jupyter notebooks available here that you can basically go and use them both first on the data that we have provided, and then you just fine tune it for your own data and for your area, and you'll have something running, which then you can go and improve and explore further. So, I mean, you can get actual cool results already just out of the box from what you take there from the code. Another interesting example is building detection. For this, you'll probably not be able to do it well with the Sentinel data because the resolution is not good enough. But I mean, this was done on spot, so 1.5 meter resolution. Here we were asked by the Azerbaijani government to help them find the non-registered buildings. So they might be non-registered simply because the registers are not as full as they would hope for, or because there are new constructions being built there, right? And they can do this now every time there is new imagery available, like every couple of weeks or every month. Yeah, they can have information of where there are new buildings popping up. Another typical problem is the object segmentation. Here, what we did is that we did the field delineation. And again, you can find a blog post describing steps one by one, and then also the source code so that you can take it and then just use it and improve it further.
Se mi fai un test audio.
Can you mute yourself? Thank you. Another example that I want to mention is a Blue Dot Water Observatory, where what we do is that we monitor about 15,000 water bodies around the world. And then whenever there is an image available, we basically extract the water body and then compare it to the nominal extent of that water. And then we just map this up, right? It's not a rocket science. The algorithms themselves are simple. Why I like this example though is that it costs a few tens of euros per month to operate this thing. So it's really cheap. So even though you have petabytes of data, you have a global monitoring. If you do it smartly, you can create models that are actually very cheap to operate, and you can then run them on a global scale without too much of an investment. And I'll actually conclude here with just a few more links so that you can copy them and explore further. And thank you very much. And I'm available for questions if there are some.
Hi, Grega. I think it was a wonderful talk, and we are really thankful that it's given such insight and technical insight to what Gilberto has been explaining. I think people are now getting a hang of what type of data sets are available, what are the complexities into the data, be it projection or the formatting, and not just that, the environmental challenges that you're going to face, be it even the simplest we consider is the cloud, but when you are actually investigating your data and training your model, this could pose a greatest challenge. And what are the machine learning algorithms that people can use, what are the Python libraries people could use? And I'm sure people can start with the EO browser that you have mentioned, people who are wanting to now start from scratch, how they can implement using EO Learn. And this is going to even need the temporal dimension. I think that is what Gilberto has also mentioned, and people are going to be able to build or train their model according to that. I think this is going to be really interesting for people, and especially I loved the line what you said is there's so much of data, but there is so little use, because getting an insight from EO data is so challenging. I think people themselves can explore once they start working on this. Thank you. Thanks, Grega. And over to you, Richard. Is it okay to start the questions? I have some questions into.
Sure, yeah, of course.
Yeah, all right. Okay, so we have one question from Neeraj. Do you think users face any challenges when they need to access EO data remotely, given the sheer size of this data?
I mean, short answer is yes, but it can be mitigated. A bit longer answer is that, I mean, if you want to do you can do a basic machine learning things from your laptop. I mean, we even have a blog post on running this Blue Dot Observatory that I mentioned, creating it from scratch on the laptop. And if you use the APIs, I mean, either Sentinel Hub or some similar ones, you can literally do this from your laptop, even if your network connection is not super strong, right? That being said, if you want to do something a bit more massive, you definitely would want to do this in the cloud, because, I mean, yeah, there will be too much of data handling, because eventually you will be processing, I don't know, terabytes of data at least. I don't think that you really need to process petabytes of data unless you really have a good reason for that. But you need to find an efficient way to extract the relevant few terabytes from that 20 petabytes of data that are available, or even more.
Thanks, Grega. Going to the next one quickly. This is a question from Jitendra. How do you label all these data? Manually doing this will be next to impossible.
Yeah, I mean, yeah. So there are just, well, there are three ways of labeling the data. One is to do it manually, and people are doing that. And the ML Hub that I mentioned previously, they really have, they sponsor campaigns to do that, and they come up with a high quality data. The other one, which we like very much, is really to just take a look into what data are available in some other registers, because you have lots and lots of this, and these data are typically updated. I mean, again, you don't need to have 100% accurate data, right? You can work with the typical accuracy of the governmental data sets, and you still can make a very good model. Then the third option is to actually create synthetic labels, as they call them, and then use these synthetic labels to train your models. What we did is that we used the global land cover 30 model, which is again a machine learning based model that was, I don't know, done by whom about 10 years ago or 5 years ago. It was I mean, they are openly available data. And even though they are like machine learning created, we still use them as labels, and we got pretty good results, which we then compare to the manual label data. So yeah, you need to be innovative. But yeah, there is some work needed, and there is what definitely there is not enough of it is sharing of the data. So like you have a paper and they would say you have 97% accuracy, but they would not share their own data so that you could you could actually check the results and maybe work on this further on. That's something that is missing in the community, and I'm hoping that it will improve in the future quite a bit.
Thanks, Grega. And there's another question from Sadaf. How do you normalize the satellite imagery before training the model?
I mean, again, you have different methods. What we do typically is that we take a temporal stack, like 1 year or 6 months. I mean, there was a very good discussion about this before. And then what we do is that we take all the data that are available there. We remove the clouds. We have a pretty good cloud detection, which again is available as an open source, S2 Cloudless it's called. And then what we do is that we interpolate between these values. And then we simply create, I don't know, let's say 10 daily slices. And then this is quite a good data set. But yeah, I mean, there are lots of innovations possible there as well.
Thanks, Grega.